Whatever happened to predictability? The milkman, the paperboy, evening TV. You miss your old familiar friends, but waiting just around the bend. Everywhere you look, there's a heart.
Today, we're going to talk about friction and why it matters to geotechnical engineers. Most failures of soil foundations are due to a shear failure. This occurs when the shear stress applied by the structure exceeds the strength of the soil. Geotechnical engineers must consider the strength of the soil while designing building foundations, embankments, retaining structures, and other earth structures to ensure that the soil beneath the structures will not fail. Frictional resistance is a mechanism of soil that contributes to the soil strength.
Coulomb's friction law relates the total shear stress at failure to normal stress, angle of internal friction, and cohesion. Cohesion is a result of interactive forces among charged particles. It is a material property of clay and some cohesive soils. The angle of internal friction is the friction angle between facing soil elements along the shear surface. Finally, normal stress is simply the force of the load divided by the area of contact. The relationship developed by Coulomb's friction law is linear and creates a failure envelope. Any normal and shear stress combination plotted below the line will not result in a failure. However, any stress combination of normal and shear stress that is plotted above the failure envelope will result in failure. Thus, we have established the importance of shear strength and the role that friction plays in determining shear strength.
Now we will discuss the most common method of determining the shear strength of soil, the direct shear test. The direct shear test can be performed using the Geotech machine found in the lab. It consists of upper and lower shear boxes that the soil specimen is placed inside of. There is a vertical normal force applied to the soil that causes a normal stress. This is held constant throughout each trial. Depending on the equipment used, either the upper or lower box is fixed and the other is moved to apply a shear stress that slowly increases. The machine measures the horizontal load causing the shear stress and the corresponding horizontal displacement. This is plotted as shear stress versus horizontal displacement to find the maximum shear stress that causes failure, which is the peak on the curve. By running multiple trials, each with a different normal stress, the graph of peak shear stress versus normal stress can be achieved. This graph will have a slope equivalent to the tangent of the friction angle and a y-intercept consisting of the cohesion component. Because the angle of friction plays an essential role in determining the strength of the soil, we designed a demonstration to show how to measure the friction angle in sand. We used what is called the angle of repose to demonstrate this concept. The angle of repose is the steepest angle at which loose soil can remain stable. We measured this by placing a funnel approximately 11 inches above a large container. We then poured soil into the funnel, blocking the end so that we could fill the funnel the entire way. We then released the soil in the funnel and watched as it formed a cone.
There's something about friction, man. It really rubs me the wrong way. I was reading this non-friction book the other day. It was really hard to grasp.
We took pictures of each cone and made some observations. We repeated this process 4 times. Each time we had a different soil with varying particle shapes and sizes. We watched how the angle of the cone that formed changed with each different type of soil that was used.
What do you get when you rub 2 oranges together? Pulp friction.
We found that soil 1 was a fine sand with angular sand particles. The angle of repose formed was 33.69 degrees. Soil 2 was a medium sand with subangular sand particles. The angle formed by soil 2 was 30.96 degrees. Soil 3 was a coarse sand with angular particles. Soil 3 formed an angle of 33.76 degrees. Soil 4 was made of round, medium glass particles. The angle formed by soil 4 was 27.93 degrees. The experiment showed how larger soil particles or more angular soil particles are able to form steeper slopes than smaller or more rounded particles. It is essential to know the steepest angle of friction a soil can form in order to design a proper slope stability to ensure that earth structures will not exceed the slope failure.
Now we will compare the cone formed by sand and clay. We started by pouring sand into a small portion of a pipe until it was full. Then we lifted the pipe quickly and observed the cone that was formed. The sand formed a neat, symmetrical cone, while the clay formed a mound that was unorderly and oddly shaped. These results were obtained because the clay has cohesive forces that causes it to form an unorderly shape, while sand experiences zero cohesive forces, so it forms a neat, symmetrical shape.
In conclusion, we observed how different types of soils have different friction angles. The friction angle of soil contributes to the shear strength of the soil according to Coulomb's law. The shear strength of soil helps create a solid foundation for structures to ensure the soil beneath them will not give out, so the structures we build can be enjoyed for the many years to come.